In today's lesson, we are going to continue our study of confidence intervals, and in particular, we're going to be looking at confidence intervals for the mean of a normal distribution when we don't have the normal approximation, so when our sample size is not particularly large. So in particular for today's lesson, what we want to see is how we construct confidence intervals for the mean when we have small n with normal populations and an unknown variance. I'll make the point here very briefly, and then I'll stop making it at this point, that today's lesson is really just a specific example of the lesson 2 lessons ago when we looked at the general construction of confidence intervals. And so we'll probably end up going through this fairly quickly, but that's because we're trying to repeat the same steps. We're trying to think about the general process, and then this is just one specific version of that general process. And so hopefully sort of this repetition ends up making these ideas clear, but try not to get hung up on this as its own separate technique. So if our sample size is too small to apply the central limit theorem, then our normal approximation is not going to be valid. Generally, we're thinking about if n is less than 30, the central limit theorem definitely won't hold. But that n equals 30 is sort of a fluid rule. Sometimes we'll want more, sometimes we'll be okay with less. If we still wish to replace sigma, because it's unknown, with s, then what ends up happening is that the underlying distribution is going to change, right? And so we'll still use this test statistic that we were looking at, where we take x bar minus mu and divide that by the sample variance or sample standard deviation over square root of n. However, this is not generally going to be a normal distribution. In general, this is going to be a t-distribution with n minus 1 degrees of freedom, which we denote with t sub n minus 1. Okay, and so we haven't seen the t-distribution yet. What does this look like? What's going on with that? Well, the t-distribution looks very similar to a standard normal distribution. However, it has heavier tails, right? So it's not nearly as compressed around the middle as the normal distribution would be. As the number of degrees of freedom grows, the normal distribution ends up being approached by the t-distribution. So what does this look like? Well, we have a bunch of sort of different dotted lines here where we're increasing the number of degrees of freedom. And so when we set the sort of solid line, which is the lowest one depicted there, that's 2 degrees of freedom. And then the top dotted line before sort of the actual sort of last line there is a degree of freedom of 30. And then beyond that's the standard normal. Right, and so we can see when the degrees of freedom are very low. So degrees of freedom 2 would correspond to a sample size of 3. Right? We can see that we're actually quite far away from the normal distribution. The shape is the same, but if you look over at how likely it is to fall around, say, -3, that solid line is way above that normal dotted line. Right? And so when our sample sizes are small, we're very far from a normal distribution. But as the sample size grows and grows, these approach one another. And this is why we can use the standard normal distribution if we have a large enough sample size. However, when the sample size is small, that approximation becomes bad. And so I'll just point out here that for any n, the t-distribution is going to apply if we're assuming that there's a normal population. Whether you have n equals 5 or n equals 500 or n equals 5 million, we could use the t-distribution. At some point, we end up using the normal approximation because it's a little bit easier and because there's not really a substantial difference. However, the t-distribution always works. The normal distribution does not always work for this situation, right? And so just to hold that in mind. Now, we can still denote the critical values from a t-distribution. They are going to be different than the corresponding critical values from the normal distribution, but you can sort of think of them as being equivalent, right? And so we can get the alpha over 2 or the 1 minus alpha over 2. And here, it's also going to depend on the specific number of degrees of freedom, right? And if we find those, what we would still find is that the probability that we fall between the alpha over 2 and the 1 minus alpha over 2 is going to be 1 minus alpha, right? And so we're back into the exact same setting that we were before, where we have our t statistic, which we take as t is going to be equal to x bar minus mu divided by s over the square root of n, right? And we know that the probability that a is less than or equal to t, which is less than or equal to b, is going to be 1 minus alpha. And so then what we do is we solve to find mu out of those things. So then we should find mu in our lower and our upper, which here, the critical values are changing. But again, that math is exactly the same. The process we're doing is exactly the same in this setting, right? So if we do that, we're going to end up with this very similar looking confidence interval here, where we have x bar plus or minus the t critical value times by the sample standard deviation divided by the square root of n. Just as before, we can use the margin of error here to do sample sizing calculations, right? And here, if we need to estimate the variance, then we can take something that would be conservative to use in that case as well. Now, this t-distribution only works when we're making an assumption about the underlying population. And in particular, it only works if we're assuming that the underlying population is normal. So remember, we talked about probability plots where we would want to test to see if things were normally distributed. This is where this starts to matter. If we don't assume that the underlying population is normal, we're not going to get the t-distribution here. And because of that, we're not going to be able to run the test in exactly the same way. There are sort of workarounds with sufficient sample sizes and these types of things, but generally the derivation of this test relies on the t-distribution coming out of the normal distribution. So when we don't know the variance, and the population is assumed to be normal, we can use the central limit theorem and large sample sizes to justify the procedure for constructing confidence intervals based on the normal approximation. If the sample sizes are going to be small, we rely on the t-distribution instead. So I'm realizing now that these summary slides have to be updated from the last lesson, but just remember, that process is exactly the same. If the sample size is small, we have to use the t-distribution. If the sample size is large, then we can use the normal approximation, but we could also still use the t-distribution. And basically what we have is the t-distribution approaches the standard normal distribution as n goes off to infinity. So in the next lecture, we'll be looking at sort of a similar thing to this, and I hope to see you all in that lesson.